We present an efficient global smoother for computational photography, a tool that requires the fundamental task of decomposing an image into a piecewise smooth layer and a detail layer. Over the last few decades, several edge-preserving smoothing operators, known as EPS operators, have been proposed. They have been applied to various computer graphics and computational photography applications. At a high level, they can be classified into two groups: local EPS filters and optimization-based smoothers. For the first class, a number of local EPS filters have been proposed to improve the smoothing quality and the runtime efficiency. Although some fast local filters have a linear time complexity, they also suffer several major limitations. For instance, it is not possible for local filters to resolve the ambiguity regarding whether or not to smooth certain edges. And this particular inability often results in halo artifacts near edges. Additionally, local EPS filters are not directly applicable to some advanced computational photography tasks. On the other hand, the second group of existing EPS approaches focuses on global optimization formalizations. These methods seek to find a globally optimal solution to an objective function through a formulation that amounts to solving a large linear system. These optimization-based methods provide the best smoothing quality with no halo artifacts, and they achieve state-of-the-art results in a variety of computational photography tasks. However, the computational cost of these methods is high, even with recently developed acceleration techniques. In this work, we combine the best of the two paradigms by proposing an efficient, high-quality, and flexible image smoothing technique, which we call the efficient global smoother. First, we present a typical energy formulation adopted in previous optimization methods, namely, an optimization using the weighted least squares framework, typically solving a linear system in the form of AX equals B, based on a large sparse matrix. This four-neighbor constraint system gives a 5-point Laplacian matrix. Though global optimization methods have proven advantageous for various applications, solving such a large sparse matrix is still not efficient, even given the recent development in acceleration schemes such as multi-level and multi-grid preconditioners. In fact, the existing global solvers are still an order of magnitude slower than state-of-the-art local EPS filters. In this work, we present an efficient technique that performs spatially non-homogeneous, edge-preserving smoothing based on the WLS framework. Specifically, we approximate the solution of the original computationally intense, large linear system by solving a sequence of one-dimensional subsystems. Here we show an example of the one-dimensional global smoother for the horizontal case. Applying the same WLS formulation to the one-dimensional case, we arrive at a much simpler linear system defined by a tridiagonal sparse matrix. Such a linear system can be solved efficiently using a linear-time Gaussian elimination algorithm. The recursive data propagation structure involved in this efficient solver resembles that of existing fast local EPS filters. However, our one-dimensional global smoother finds an exact and global solution to the objective function in a principled way, and it's this global optimization nature that proves to be critical in achieving high-quality results. The proposed one-dimensional smoother can then be leveraged to solve the global smoothing optimization problem defined over a high-dimensional domain. Here we focus on the two-dimensional image smoothing and its wide applications. Similar to some state-of-the-art local filters, such as domain transform filters, our two-dimensional global smoother consists of alternating the efficient one-dimensional global smoother along the horizontal and vertical directions iteratively. This separable implementation not only provides close approximations to those of time-consuming exact global solvers, but it also brings in the essential advantage of a linear time smoothing efficiency. To illustrate the limitations of local smoothing filters and the advantages of global smoothers, we first present the results of smoothing a simple synthetic image. It can be seen that both the original WLS method and our global smoother nicely remove the noise while preserving the sharp edges. This is in contrast with other local filter-based methods, which have to trade off their edge preservation capabilities with smoothing strength, resulting in annoying halo artifacts. Note that our method is about 20 times faster than the WLS method. Here is another example of smoothing a natural color image. Now we report the timing results for smoothing a 1 megapixel RGB image using a single CPU core. The guided filter, the recursive filter of the domain transform method, and our method take 0.3, 0.09, and 0.12 seconds, respectively. The global WLS method, using a recent sparse matrix solver, still requires about 3.3 seconds. Therefore, our method has a runtime efficiency comparable to fast local filters, and is much faster than the WLS method. Our method is robust and versatile, so it can be applied to many computational photography applications, some of which cannot be adequately handled by local filters. Now we demonstrate the effectiveness of the proposed efficient global smoother in a variety of applications. First, our global smoother is used to manipulate image details by decomposing an image into several scales and recombining the decomposed signals. Our method achieves comparable results to the original WLS method, but with a much lower runtime. We also apply our smoother to structure-texture decomposition, which was originally formulated by solving a series of linear systems in a way similar to iterative reweighted least squares. The quality of the two methods is similar, but ours is much faster. We can conclude that our solver is useful in some tasks when using the general LP norm as well as the weighted L2 norm. Note that this kind of application cannot be directly handled by local filters. A next application is image colorization based on sparse user inputs. Here, our solver also achieves an indistinguishable quality to the global optimization method. Now, we demonstrate how to handle imprecise color scribbles in an image editing application using our framework, while still maintaining a computational advantage. When rough or imprecise color scribbles are provided by a user, existing colorization methods may produce serious color smearing artifacts, since the data constraint is imposed in a rigid manner corresponding to a uniform reliability matrix, or namely, the identity matrix. So, the conventional schemes based on such a hard constraint exhibit color bleeding artifacts, even after several iterations. In contrast, thanks to the flexibility of our formulation, we can address such erroneous inputs in image colorization by employing a robust data constraint. The new data constraint gathers neighboring input data and thereby determines how reliable the input data is. It can be expressed in a matrix form as shown here. This good quality is achieved by using the two soft terms D and CF defined in a spatially varying way. Achieving a much better quality and robustness for the imprecise user edit scenario, our extended optimization formulation can also be efficiently solved largely in the same way as the basic version, so the computational efficiency is not compromised. This is particularly important for interactive image editing applications, as instant edit feedback, high-quality results with limited or even rough user interaction, and fast convergence are all desired. Here is another colorization example, highlighting the problems of various existing methods.